So, hello everyone. My name is Amy Burt. I'm the programming coordinator with Wildlands Trust, and I want to thank you all so much for coming on to our Principles and Guidelines for River Herring Counting Programs presentation tonight. I'm super excited to have you all here as we get into the river herring counting season. Um, Perhaps if you have done river herring counting before, you'll be a little more familiar, but perhaps we have some new people joining tonight as well. So for those of you who are not familiar with Wildlands Trust, we are your regional land trust protecting land across southeastern Massachusetts. Currently, we serve over 55 plus different cities and towns and protect over 14,000 acres of land. We protect, steward, and connect people with the land across southeastern Mass. If you are interested in learning more about our trails, our preserves are free and open to the public year-round from sunrise to sunset. We have guided hikes on our properties, and you're welcome to come out with me, or perhaps you might join one of our volunteer hike leaders. We have different events like this. We have online presentations, we have in-person presentations at our community conservation barn, and we also have events across our service area. I want to thank the Herring Ponds Watershed Association for coming out tonight to align this program. And I'm going to turn it over to Don Williams.
Okay, my name is Don Williams. I'm president and co-chair of the Water Quality Committee of the Herring Ponds Watershed Association. We are delighted to be here and present at this presentation, and I want to thank Amy and Wildlands Trust for doing this for us, with us. I want to thank my wife, Jerry Williams, for arranging this. I want to thank John Sheppard for taking the time to educate us. And I'd like to thank all of you for coming. A few words about the Herring Ponds Watershed Association. We take care of 4,450 acres, which consists of 11 ponds and about 2,000 homes. The main focus is on Little Herring Pond, Great Herring Pond, and Elbow Pond. And we are here to preserve and protect the water and the land. We're all volunteers. There's 270 members and 500 on our mailing list. This is a map of our domain and a map of the Watershed Association area. And we were founded in 2007, so we've been doing this for quite a while. We've been collecting water samples for quality since 2008. We have a great partnership with the E&E department now of Plymouth, and we have used them as helpers to get us a water quality plan to help us make our watershed a better place to live. We've done a number of things. I just want to highlight upcoming things, and those are our Herring Count Festival on April 25th at Brewster Park. It's a great opportunity for children and adults to learn about the herring because we have a herring obstacle course that's wildly popular. I also want to let people know that there's a boating safety course being scheduled for April 6th, 9th, 13th, and 16th from 6 to 9 p.m. These are obligatory for people who have boats. Eventually, you're going to have to get this course. So if you're members of the Herring Ponds Watershed Association, you can apply for membership to join this. Let's see. Here we go. We have had a major battle with cyanobacteria. It started with 2020, a major bloom. 3 out of the last 5 years, we've had blooms. Phosphorus is the problem. We found this out from our water quality plan, which was done with the partnership of Plymouth. We think that we know that the largest single source of phosphorus that goes into Great Herring Pond comes from Little Herring Pond. We've tried one thing. We put a permeable reactive barrier in Carter's River to capture the phosphorus before it got to Great Herring Pond in the summer of 2024, but it did not work. And so we didn't take enough phosphorus out, and we're going for a plan C at this point. I want you to know our board of directors, myself, Michelle Christensen is our vice president. Brian Harrington's our treasurer. Brian's also on the board of Wildlands Trust, by the way. Cheryl Lewis is our secretary. Teresa Durr is our membership chair. Jerry Williams, as you probably know, is our outreach communications chair. Beth Sobolov is our communications committee chair. Jack Kedian is my co-chair with water quality. Jerry Levine does invasives. Tom O'Brien is water safety. Trish O'Brien is our social committee chair. Paul Denoncourt's the assistant treasurer. Tess Goldman, who works for the Wildlands Trust, is our education committee chair. Melissa Ferretti is a member at large, and Lynn Ortell, that you'll learn a little bit more about, is in charge of our herring count. So John Sheppard, whoops, wait a minute, here we go. John is a diadromous fisheries biologist. These are the fish that come from the saltwater to spawn in this freshwater and return to the saltwater after doing so. He will talk about the principles and guidelines for river herring counting, a valuable service that we also perform. So, John, tonight we will hear from an expert. We will hear an inspiring story about a remarkable fish. And these fish drive a valuable New England industry, which is commercial fishing. And you can help. More about that later. John grew up in Boston. He's a lifelong fisherman and outdoorsman. He has a master's degree from Aberdeen, Scotland, in marine and fisheries. And he is now involved, as I said earlier, with Diadromous Fisheries. Lynn Ortell is our Herring Ponds Watershed Association herring count information volunteer. She can be contacted if you want to volunteer to count, and she can be contacted if you have questions. I have her email up. It's lbortel, OERTEL, at comcast.net, and her phone number is 774-217-3178. And with no further ado, John Sheppard, the movement goes to you. Thank you.
Okay, so thank you, Don, for that introduction, and thank you all for having me. For myself, I'm a diadromous fisheries biologist, and I oversee several monitoring programs here in southeastern Massachusetts, where I monitor primarily river herring, as well as American shad, and to some extent, I also participate in monitoring for American eels and other diadromous fish as well. I oversee several monitoring programs, primarily in Bristol and Plymouth counties here in Massachusetts, whereas some of my other colleagues cover other regions of coastal Massachusetts here. For river herring monitoring, I also work with volunteer counting groups and coordinators, whereas these groups will go out, they'll collect data primarily using methods such as visual counting. They'll send that data to me for processing, analysis, and then I'll report those results back. So for my presentation today, I'm just going to give a brief description of the life history of diadromous species, in particular river herring. I'll also discuss their ecological function in aquatic ecosystems. I'll talk a little bit about their historical and current importance, and as well as their current population status. And with that, I'll talk about our monitoring programs here in Massachusetts. And with that, I'll have an emphasis on conducting visual counts. And so I'll go over various principles for conducting visual counts. And some of this will be statistics based, but I'm going to try not to go too heavy on that. I don't want to disinterest or put anyone to sleep or bore people with it. But with that, I'll talk about our counting software program, how we process and analyze that data, and for quality assurance and quality control. Um, but with that too, I'll also talk about the various limitations that are associated with visual count data, and then I'll present some case studies here of some uh, watersheds here in Massachusetts that have some really great counting programs, and then I'll conclude by just summarizing and some recommendations. So first, I just want to talk about the life history of diadromous species. So what is diadromy, or in this case, what are diadromous fish? And these are fish that spend portions of their life cycles in freshwater as well as in the marine environment. There are many forms of diadromy, but there are two main categories. One is being anadromous fish, and these are fish that they're born in fresh water, but they spend the majority of their lives at sea, but they will then return to fresh water for spawning. And so some of the most common examples of that here, especially in Massachusetts, are river herring. And the diagram below shows their life cycle here, as well as their larger cousins, the American shad, and one of their more high-profile species here in New England, the Atlantic salmon. Now, there's another form of diadromy. It's essentially the opposite. They're called catadromous, where they're actually born in the ocean, but then they migrate to fresh water and live to maturity and then go back to the ocean to spawn. And so our most common example of that is the eel. Now, with that, with diadromous fish, they essentially have two, you could also call it two other categories. One is being, and what we see, especially here with river herring, is that they are known as iteroparous, which these are fish that are capable of spawning multiple times throughout the course of their lives. And we can actually see that in their scales as we go to age them. We can actually tell the spawning history of a fish and times when they've actually come and come to fresh water to spawn and what age they do that. And then there are other species such as when you think of West Coast salmon, they are known as semoparous, which, after they're born in fresh water, they go out to the ocean. And then when they come back to fresh water, they die after spawning. And as a matter of fact, eels, even though they're catadromous, they actually are semoparous as well. They can live anywhere from 5 to up to 20 years in fresh water before migrating back out to the Sargasso Sea, where they'll spawn and then die after spawning. And so river herring are essentially comprised of two species. They are the alewife and the blueback herring. Externally, they're nearly identical, and so they're very difficult to tell apart. Typically, for alewives, they tend to be larger than blueback herring, and then looking at them externally, they tend to have a larger eye than blueback herring do as well as a subtle little hump on the top of their heads, just behind the eye, that is lacking in blueback herring. And so, but the most definitive way to really tell them apart is actually internally, when you actually look at the color of their body cavity. The alewife actually has a pale to light colored body cavity, whereas the blueback herring is dark inside. And so the maps on the left show the geographic range of both species. And so alewives, which is the pink region on the map, they can range as far north as Newfoundland and Labrador, as far south as South Carolina, whereas blueback herring range from Nova Scotia down to mid-Florida. And so because their regions overlap, they often occur together in many coastal rivers. And because of that, they occupy different spatial and temporal scales. And so as an example, like alewives tend to enter rivers, and I should say in watersheds where both species exist, alewives tend to enter the rivers first. Here in New England, they tend to enter the rivers when the water temperatures get around 10 degrees, and their preferred spawning habitat is the slow-moving waters found in ponds and lakes. Whereas blueback herring will tend to enter the rivers a little bit later when the water gets a little bit warmer, say around 14, 15 degrees. And they prefer to spawn in more riverine sections, flowing water areas in rivers. And so this difference in the temperature and the habitat, it helps to limit, you know, competition between the two species for food and for habitat. So river herring, they serve important functions in both freshwater and in marine ecosystems, particularly in terms of energy transfer from producers to consumers in both food chains and food webs. And so I have a couple of examples here. We have a food pyramid on the left and a simple food web on the right. Um, now, river herring, they tend to serve as what we would call a secondary consumer. And you can kind of see that in the food pyramid there, where they'll feed on things such as zooplankton and small, arthropods. And in turn, they actually serve as forage for higher trophic predators. So in freshwater, you think of species like largemouth bass, say pickerel and northern pike. And then, uh, various avian predators, from gulls, cormorants, and ospreys, even eagles. And then out in the marine environment, they serve as food resources for, some of your high profile game fish like cod, bluefish, striped bass, uh, tuna, and even marine mammals such as seals. But more importantly, too, river herring also serve as vectors as because they transport nutrients from the different environments. From the adults bring in nutrients from the marine environment into fresh water during their spawning migrations, and then juveniles, as they're emigrating back out to sea, will bring nutrients from fresh water into both estuarine and marine environments as well. And so this transfer of nutrients from one environment to the other, it helps stimulate the base of food webs. It helps support, primary production, which then supports higher trophic levels. So next, I'm going to talk about the historical and current importance of river herring for us folks. And so prior to colonial settlements, river herring served as an important seasonal component in the diets of Native Americans, as they would move from inland areas in the winter to coastal areas in the spring, to set their nets, to set their weirs, and for the harvest. And river herring, they also serve as some of the earliest documented commercial fisheries here in North America. The first commercial fisheries in the U.S., they date back as early as 1633, where river herring were harvested as food, and the surplus was either stored for future consumption or exported to newly created domestic markets. In fact, for a brief period during World War II and afterwards, river herring were actually utilized in the manufacturing of artificial pearls. So today, commercial fisheries still exist in some states, where they, for example, in Maine, they're harvested as bait for the lobster fishery, but they can also be used for things such as pet food as well and fertilizer. So when we look back at the last century, um, the graph to the left here shows the commercial landings for river herring here off the continental United States. And so these landings, they peaked after World War II, and the fishery at the time was prosecuted primarily by foreign fleets that were fishing off the U.S. coast. And so these peaks and landings, this was also in part due to the transfer of what was at the time military technology. When you think of sonar and radar used by the military, it was then transferred for use by the fishing industry. And so As you can see, the landings declined in the 60s, and with the passage of the Magnuson-Stevens Act in 1976, this established a 2-mile exclusive economic zone, which moved the foreign fleets outside of coastal areas. And so, however, despite this, landings continued to decline, and by the turn of the century, coastwide populations had declined over 95%. And so this eventually led to closures in individual states, such as Connecticut in 2003, followed by Massachusetts and Rhode Island in 2006, and then eventually coastwide in 2012. And since that time, there have been a couple of attempts to petition river herring to be listed by NOAA as threatened or endangered under the Endangered Species Act. However, assessments that were conducted by NOAA for both of these cases indicated that listing was not warranted, and this was largely due to recovery in certain areas of its coastal range. In 2024, the latest benchmark stock assessment for river herring found coastwide populations remain depleted relative to historic levels, and they identified several factors that have been hindering recovery efforts. These include overfishing, habitat loss, predation, pollution, and climate change. And so between 2000 and 2006, here in Massachusetts, we experienced significant declines in river herring populations coastwide here in Mass. And so as a result, harvest and possession was prohibited in Massachusetts. But this also led to a growing public interest in the status and conservation of river herring here in Massachusetts. And so community groups at the time, established visual counting programs at several rivers. However, few of them were able to use proper statistical sampling techniques that were required to produce reliable estimates of abundance. And so in response to this, DMF, my agency, we hosted a river herring counting workshop in 2005. And the results from that, we published a technical report describing methodologies on how to estimate river herring abundance using visual accounts. And with that, we actually followed that up with 2 other workshops, one held in 2024, and then one held last year, where not only did we review visual counting methods, but we reviewed other monitoring methods, and we developed standard operating procedures for each of these. And so with that, I am gonna talk about these different monitoring methods, but I'm going to focus primarily on visual counting. And so with our standard operating procedures, the objectives that we had for these programs was to guide community watersheds and groups that were currently conducting or starting visual counting programs. We wanted to provide recommended sampling designs and protocols that would help produce statistically reliable estimates of abundance. And with that, it was our hope that we could review and consider data for both state and for federal stock assessments. And so the Atlantic States Marine Fisheries Commission, which is the entity that helps to manage migratory fish, including diadromous fish, they've established certain biological criteria to identify river systems that would represent the regional and coastwide status of river herring populations. And so they came up with essentially 2 criteria. One is a minimum 10-year time series of abundance estimates, and then where possible, that data would be augmented with biological data or population demographics data. And so this list here, this shows that currently, Massachusetts has 11 rivers that are represented in the most recent river herring stock assessment, of which 2 of them are monitored exclusively using visual counts, and then we have several others that are monitored using both a combination of visual and other counting methods as well. And I will say that having this many streams represented in the stock in the stock assessment is quite remarkable for a state and really is a credit to, especially to citizen scientists, because for their valuable contributions towards this process. So next, I wanted to talk about our monitoring program here in Massachusetts. So in terms of monitoring for river herring, this goes back as far as 1980. And so if you look at the map of the state above, you'll see that the coastal area is divided into major coastal drainage areas. And so our strategy is to have at least one, what we would call index or sentinel monitoring site in each one of these major coastal watersheds that would be monitored, of which the data produced would be used to represent the stock conditions for each of these major drainage areas. And so these sites, these index sites, they're continuously monitored, primarily using either electronic or video counting systems, but other locations that are monitored within these major drainage areas also provide supplementary information on populations within each major watershed. And so if you look at the map on the left, this and the table down below, this is actually a map and summary statistics for herring counting in 2025. So in 2025, we had 48 locations that were counted using a variety of methods. But of these methods, visual counting is the most commonly used method. It comprises over 60% of all locations monitored. And so citizen scientists, they make significant contributions to monitoring and counting. So in 2025, 90% of the streams were either monitored solely by volunteers or with volunteer assistance. So for our monitoring methods, we primarily use three methods. Those are shown here, and I'm going to talk primarily about visual counting, but next I will talk a little bit about electronic and video monitoring systems. So for the three methods here, they have advantages and disadvantages to each. And so first I'll go over visual counting here. The big advantage for visual counting is that in terms of equipment, it has very, very low startup costs. I mean, really, all you really need is, maybe like a manual hand tally for recording numbers, as well as, a notebook with data sheets. If you have a thermometer, you can use that to collect, air and water temperature. Now, if you conduct your visual counting program if you use consistent, sampling designs and methodologies, you can produce reliable estimates of abundance with it. And, visual counting programs is also a great tool for both public outreach, for public education, as well as stewardship for local resources. It does have its disadvantages. In comparison to other methods, the estimates from visual counts, they have a lower degree of accuracy. It does require a considerable amount of effort in terms of producing enough counts to produce, reliable estimates. And it's also very challenging to maintain, volunteer effort as well as coverage over time. Now, next, I'm also going to talk about electronic counters. Now, electronic counting systems, the big advantage is that they have highly accurate estimates of abundance. If operating properly, you can have estimates that are, 90% or even higher in terms of accuracy. They have the advantage in that they can provide continuous counting 24 hours a day, 7 days a week. And unlike visual count or video counting systems, electronic counters, they're not affected by water clarity or visibility in the water. Now, they do have their disadvantages. For one thing, they have high startup costs and maintenance costs as well. And actually, as I will say that they actually are no longer being manufactured. It's actually regarded as obsolete and outdated technology. So the one company that actually produces these systems no longer produces them. So eventually, when these systems, the ones that we oversee and manage, once they fail, we're going to have to look to alternatives for monitoring. Um, Other disadvantages include that they require daily maintenance. They have to be checked every day. They also require continuous power in order to operate. And in rivers and streams that have multiple species that move and migrate, the electronic systems don't have the ability to distinguish, between species. Now, with video like electronic counters, they can produce highly accurate estimates of abundance. They also can count continuously, and especially in areas where you have viewing screens, it's a great tool for public outreach because people can actually watch the fish as they're passing, past the camera. Um, they too have their disadvantages in that they are moderate to high startup costs. Um, but despite the fact that technology is continuously becoming cheaper, still they have very high power and especially storage requirements to operate these systems because you have to have computers there. And, as you're recording the footage, that has to be stored onto hard drives. And then you have to, oftentimes when you're out in the field, you have to swap out those hard drives and then upload those data. And you have to make sure that you have very high storage capacity for all that video. Like electronic counters, they require daily maintenance. But I think one of the big disadvantages for video systems right now is the amount of effort that's required post processing, which, basically, having people to review and manually count fish. Because this is often done after the season's done, and so even with today, there's been advances in terms of the fields of AI and using machine learning. It's research that we're currently involved with right now. It's still in it does show promise with using AI and machine learning to actually automate the counting process, but it's still in a developmental stage, and until this technology becomes perfected and more, widely, available for distribution, unfortunately, you have to have some poor soul sitting sitting in front of a TV watching hundreds of hours of footage to come up with your estimates. So I next want to talk about our main focus here, which is visual counts. And so first of all, I want to talk about, what are the numbers that are produced by visual counts? What is in a visual estimate? Well, to start off, and to be blunt, visual count estimates, they are not a true estimate of the total population or total run size. Um, Rather, the estimates that you derive from visual counts, we refer to them as indices of relative abundance. And so, why is that? Um, the reason being is because the counts are conducted typically during a specified daily observation period. They're typically done during the day, and so when you do that, you then basically you have a set daily observation period, and then you randomly conduct counts during that period, and then you have to extrapolate based on your sample observations to come up with an estimate. Now, because because of this type of method, your estimates are going to have a higher level of variance and standard error in comparison to electronic counters and video monitoring systems. Now, people ask, why do you randomize your counts when you do it? Well, this kind of goes back to the basics of statistical and sampling theory. We randomize our counts because we want to reduce bias in our results, and so that basically means that random sampling, it avoids unintentionally choosing individuals that might favor a certain outcome or skew your results towards a particular result. And what I mean by that is um, it prevents you from like going during certain times, especially if maybe if when fish are running, and then trying to concentrate your efforts during the times only when they're running. That actually can bias your results. So if you do so with random sampling, if you do it that way, it allows the use for statistical methods so that you can calculate not only means, but also confidence intervals and to assess the significance of your findings. And so I have a graph here. This shows these are actually visual counts that were conducted at Pilgrim Lake in Orleans. This is a count that's conducted from 2008 to 2024. And so really what you're doing here is your counts are actually, these are indices of abundance. And so if you do it in a scientifically sound manner, you can then track abundance over time, and then you can actually use it to identify trends in your population. So next, I want to talk about where to conduct your visual counts. And so, when I think about, when I think about this question, I often think about, when I went to, look for my home. I remember asking my father at the time, what's the most important thing to think about when you're looking for a home? And he told me, well, it's three things: location, location, location. And I'm sure many of you have heard that too in your hunt for homes. But I think it applies to visual counting programs too, because the location of your counting station is going to have a very important say as to what type of estimate of abundance that you have or that you're looking to achieve. And so here I have three maps showing three different examples here. So the one on the left, this is actually our local watershed here. This is the Monument River watershed. And you'll see that the dark circle at the bottom here, that's the location, excuse me, of my counting station, which is an electronic counter that's at the ladder exit to Foundry Pond. So this is right down near where the river empties into the Cape Cod Canal. And so, this watershed has both alewives and blueback herring present in it. And so because it's located right near where it empties into the canal here, the index of abundance here, where is basically assumed to reflect that for the entire population for the watershed, because it's so close to where the outlet is. And so it's not a census population, but it's pretty close to one, because there are inherent biases and errors with electronic counters. Now you'll notice there's a red circle here, and I'm also going to use, that's the location for Great Herring Pond for the visual count, but I'm also going to compare that to the one in the middle map here. This is the Nemasket River in Middleborough. The Nemasket is a tributary of the Taunton River. And you'll notice that the counting station, the dark circle, it's actually midway between where the river actually empties, where it actually flows out of the Assawamsett complex, and then where it actually joins with the Taunton River. And so here, this location, we would refer to the estimates here as an index of partial watershed. Which means that basically, this river has both alewives and blueback herring as well. But based on our biological sampling that we collect here, the alewives that the herring that pass beyond the station here are exclusively alewives. So we know that there are blueback herring present in this watershed. They just don't make it this far up. So it's not. So the estimates are not, an estimate for the total population or for the entire watershed. Rather, it's an index for the partial watershed, or sometimes people will refer to it as escapement. So when you go back to the first map and you look at the location for Great Herring Pond, this would be the count there is an index of the partial watershed, because we know that the alewives are passing, they're entering into Great Herring Pond, and they're even going further up into Little Herring Pond, whereas the bluebacks tend to prefer the more riverine sections for spawning. So many of them will not get up as far as Great Herring Pond, but they'll spawn in the downstream reaches and sections of the river. And then finally, the last map here, this is the Acushnet River watershed. This is a watershed that's undergone a series of restoration efforts where improvements to fish passage at various points in the watershed, and the counting locations up at the New Bedford Reservoir. So for this one, the estimates that we derive here, we refer to this as a restoration response because we're basically looking to see how many river herring are getting up as far as to the reservoir as a result of improvements to passage downstream. So what I want to do next is I want to just kind of go over kind of a simplified version as to how the visual counting program is conducted. And so the initial concept for estimating river herring populations using visual counts was conducted by a gentleman named Rideout, and this was actually part of his graduate research. He did this on the Parker River up in northern Massachusetts, and the Parker River is one of the rivers that is represented in the coastwide stock assessment. And so the diagram here, it summarizes the basic concepts of Rideout's sampling design, in which what he did was, if you look at the x-axis, that's time, which is basically, that's your spring spawning period. And then on the y-axis on the left, that's basically the time of day. And so each day of the spawning season, he divided it up into sampling periods. In this case, it's hours per day. And so next, what was done was that visual counts would be conducted randomly each day throughout the spawning season. And so if you look at this graph here, you'll see that there's a blue curve in the graph. Think of that as your theoretical river herring population. And so any of these shaded squares that are inside the curve, think of those as counts where fish were actually observed passing. And then the squares, the shaded squares outside the curve, think of those are ones where counts were conducted, but no fish were actually observed. And so estimate, the number of fish that passed each day. The counts were conducted randomly each day. And so I grabbed one example here. Let's say on day X, 4 counts were conducted. And so 3 of these counts lie within the curve here. So these 3 counts actually observed fish, and then we had 1 count where no fish were observed. So the first thing that we would do is we would calculate what is the average number of fish that pass per hour. Now, if these are 10-minute count intervals, and 4 of them were conducted, you would add those numbers up, and then you would divide it by the total number of samples that you took. In this case, it was 4, and then you would come up with a mean number of fish that passed per 10-minute interval. You would then extrapolate that number to estimate the number of fish that passed per hour. And then what you would do then is you would further extrapolate it again to estimate the number of fish that passed for your daily observation period, which in this case, this was conducted from 7 a.m. to 7 p.m. So it's a 12-hour daily observation period. So you would take your number of fish per hour, multiply that by 12, and that would give you your estimated daily passage. So then to figure out total abundance for the season, that would be the cumulative sum of your daily estimates or your estimates of daily passage. So that's kind of a simplified version of Rideout's method. And so some counting groups, they tried to adhere to his sampling scheme, but the required daily coverage and the number of hourly, sampling that was required to achieve this, couldn't be done. It was largely either due to, not having enough volunteers or scheduling difficulties. And so for these reasons, one of our statisticians here at DMF, Gary Nelson, he conducted a review of basic statistical concepts, and he used this to develop alternative sampling designs that could be used by volunteer groups to estimate river herring abundance using visual counts. And so he provided this all in his technical report. And so this provides guidelines to define sampling periods as well as the number of of counts that to be conducted within each period. And so there are three examples that are shown here. The one on the left, which is figure A, this is what we call a one-way stratified random sampling design, where if you say you have a 12-hour daily observation period, so in this case from 7 a.m. to 7 p.m., to meet the requirements for this sampling design, you would have to conduct a minimum of 2 counts. But because it's such a low sample size, the extrapolation, there's so much so much time that has to be extrapolated out that the results produce a much larger variance in your estimates. And so for that reason, we generally don't recommend this sampling design. It can be done, but we generally don't recommend it. If you look at the middle example here, this is what they call a two-way, two-period sampling design, where if you take your 12-hour daily observation window and you divided it to, say, 2 6-hour periods, and then you conduct a minimum of 2 counts randomly within those 2 6-hour periods, it gives you a minimum of at least 4 counts per day, and it actually the accuracy of your estimates is greater than it would be if you were using a one-way design. And then if you look at the third example here, this is what we call a two-way, three-period sampling design, where you take your 12-hour window each day, but you divide it up into 3 4-hour periods. And then if you conduct a minimum of 3 random counts within each one of these 4-hour periods, so you would have a minimum of 9 counts per day. This actually produces a higher level of accuracy, and it lowers the variance in your estimates. And so this is generally the design that we recommend for visual counting groups if they can do so. So along with these different sampling designs that Gary reviewed, he also developed a visual basic program that can actually help you estimate river herring abundance, based on the data that you collect. So this is a visual basic program. This just shows some of the displays and some of the outputs that that the program produces. But in order to run this program, we essentially need 4 sources of input data. We need the date, the time that you started your count, the time that the count ended, and the number of fish that you actually observed in your count. So that's the data that's required to run the program. Now, the program can also generate summary statistics on environmental data, for example, like water temperature, air temperature, weather, flow. I mean, if you can record that data, that could be very useful data, but it's not essential for to actually run this program. And I'll go into some more detail on this program in the next slides here. Now, one of the great features of this program in terms of quality assurance and quality control is that the program can check for and identify errors in your data, and it can allow the user to actually edit and correct individual entries before conducting your analysis to estimate, daily passage and total abundance. The program also tests the statistical ability of your estimates to detect population trends, and this uses a feature called a power analysis. So in this case, what is power? The power is the ability to detect changes when they are occurring, and so in this case, the power analysis examines the probability of being able to detect change over time given the level of sampling intensity that you use. And so if you look at the graph on the left, what you see here is on the x-axis that looks at the percent change over time, and then the y-axis is basically what you call your predictive power, your probability of being able to detect change. And so you see 3 curves on this graph here. Ideally, what you want to see is they're V-shaped curves, and ideally what you want to have a steep V-shaped curve. The steeper your curve, that's the higher the probability of being able to detect change, as well as the more likely you'll be able to detect change over time. And so I'll show some examples of that with some of my case studies and some of the other simulation exercises that Gary conducted. So, in Gary's review and his analysis, he also looked over various sources of error and how this can affect your estimates. And so the following figures here, these are theoretical examples to demonstrate the effect of sampling size and sampling frequency on the accuracy of your abundance estimates. And so these were based on simulation exercises that Gary conducted, taken from a theoretical run of a known population size, and then conducting, 10-minute counts, that were randomly selected for each day. And so for example, the graphs here, they show the results of each of these simulations. These are represented by a mean along with 95% confidence limits. And so if you look at the one at the top left, this is figure A. This shows the effect of sample size on what they call precision. And so what you'll notice here is if you have a theoretically known run size, this one looks like it's a population of 125,000, it shows that as the more samples that you conduct over the course of a day, the precision and the accuracy of your samples increases with increasing sample size. Now, if you look at the graph below it, this is figure B. This actually shows the effect of what we call aggregate or pattern sampling. So let's say, for example, you have a run where I can only go out and sample in the afternoon. I can't go out and sample in the morning. So I go in the afternoon and I conduct my counts. Well, what happens is that what the results show is that even with increasing sample size, and it shows that that the precision of your samples actually increases, the accuracy of your samples actually doesn't. And the reason being is because you're only sampling during one specified period. It's basically when you conduct the extrapolations, it's assuming that in this case, I'm only sampling the afternoon. When you conduct the analysis, it's assuming that passage during the morning is the same as it is in the afternoon. So what winds up happening is you're overweighting or you're overinflating your estimates, in the morning. And so that's a source of bias. And I'll actually show some examples of that in some of our in some of the slides that I have coming up. Now, the four graphs on the right here, this shows what happens when you to the accuracy of your estimates if you miss sampling. For example, in the upper left, one day of where samples were missed, 2 days, 3 days, and 4 sequential days. And what you see is that your confidence limits, they get larger, the more time that data hasn't been collected or counts haven't been collected, because with the larger gaps in time, the program has to extrapolate more. And so the more it has to extrapolate, the higher the variance and the more, the larger the standard error will be in your estimates. So these are a few statistical examples of some of the things that we see, and the different factors and how they impact, your not only your estimates, but in particular, your ability to be able to detect, trends and change over time using the power analysis. So the one up at the top, this is actually, we oftentimes see this where you have a run that has a very small population, because oftentimes what happens is these fish are only moving during very brief specified periods. And so, which you kind of see on that graph, you see a spike, and then after that, it mostly tapers off. You see a little bit of activity here and there, but most of the passage is occurring over one brief period of time. And so, because of that, it's hard to really, get a very highly accurate estimate, because you'll have one period of time where you might be getting a bunch of counts, and then the rest of the time you're getting very few or very sparse, observations where you're actually seeing fish. And so because of that, you'll see the graph on the right, to the right of it, that's the power analysis. You see that, rather flat V-shaped curve. And so under this scenario, it's difficult to actually accurately, detect change over time. Now, the middle example here, the graph, this is often, we see this with a lot of runs where, we're basically, this is the effect of low sample size on in producing accurate estimates. In this case, you're seeing that there are many days where you're not even getting that minimum 2 counts per day, as well as several days where there are missing counts, where counts weren't conducted. It's through no fault of any volunteer group. A lot of times it's just, there just aren't enough people, or, they have a small group of very dedicated people, but they can't get out there to count all the time. And so, because of that, you see that in the power analysis as well, is that, it produces estimates that have a high degree of error and a low probability of being able to detect change. Now, the example on the bottom, this is an example of what we call patterned or aggregated sampling. So this is a run where, based on historical information, there's a lot of activity that occurs like right around sunset, right around dinner time. And so because of that, the coordinator for the group, he would actually concentrate his volunteers and send them out, primarily during that time to go out and count, because the person knew that, in all likelihood, that's when the fish were running. So what you see is a high number of counts that are being conducted during dusk, and then sparse, counts during the rest of the day. And so that also affects your precision and accuracy as well as your power, because basically you're waiting, a brief period of the day and extrapolating that over the course of the entire day. But we know that, fish don't uniformly pass like that. So that's, like I said, this is one of the things that we try to encourage groups to avoid is, patterned or aggregate sampling. So, as a result from that first workshop, Gary had come up with the following recommendations: that programs would follow a two-way stratified random sampling design, where they would divide, their daily period into three periods, and then make a minimum of 3 10-minute, counts during each of those 3 periods. And that counts would be conducted throughout the entire spawning run. And so after about 15 years, DMF, we actually conducted an internal review of all the visual count data from all sites and for all years counted. And so we did this review primarily to determine the reliability of these estimates, as well as to identify any data sets that could be potentially included into both state and coastwide stock assessments. So our review, we identified errors and inconsistency and count metrics. And where we did find these inconsistencies in these metrics, we standardized these metrics so that they would be consistent. And then once we standardized these metrics, we then re-estimated, these counts and then produce new estimates of abundance. And in which case, in some years, where if we saw real substantial departures from these newly standardized metrics, some years we had to actually remove data. So I'll show you an example of that here. So for each of these runs, we generated summary statistics for all years where monitoring occurred. And so this example here, this is the Herring River and Wellfleet. These are visual counts that were conducted from 2012 to 2000. In this case is 2023. But what we did was we the parameters that we examined to standardize, they included, the first day of counting, the last day of counting, so that we could get a standardized, duration, as well as the number of, we also looked at things like the number of days where there were missing counts and number of days where there were an insufficient number of counts. And then we also standardized the start and end times for the daily observation periods. And so we then developed newly standardized metrics by finding a consistent range for each of these sampling strata. In this case, looking at the daily observation periods, which is shown here on the left, as well as the number of days that were counted, which are shown on the right. So if you look at these two graphs, the regions that are highlighted in yellow, this is the data that we actually standardized and included. So, the lines that are outside these yellow regions, this is data that we would actually we actually omitted when we reanalyzed and re-estimated. And so this example here, this is a group that actually did a really good job over the course of their monitoring. And for that reason, the Herring River and Wellfleet, this was a newly added data set to the coastwide stock assessment. And so once these metrics were standardized, we then re-estimated both daily passage, which is shown on the left, these graphs on the left, and then the total abundance, which is shown on the right. And we did this for all locations for all years monitored. And so in this example here, again, this is Herring River and Wellfleet. The daily counts on the left and the estimates of abundance on the right, these are based on observations conducted, within a consistent time period, say between April 1st and May 25th each year, between the hours of 7 a.m. and 7 p.m. So the one thing I do want to talk about is I want to talk about the inherent limitations of visual count data. Visual counts have several limitations. As I mentioned before, they're not true population estimates. These are referred to as indices of abundance, and it's basically because these are based on a set daily observation period, and also when we standardize these metrics, there are times when we have to censor or remove count data, just for maintaining the sake of consistency. Now, the newly standardized metrics, they don't account for changes in phenology. And so in this case, it's changes in spawning migratory patterns. And I'm actually, in the next slide, I'm going to go into more detail about this. So I'll come back to this. These standardized metrics, they don't account for changes in deal migration patterns, which you think about changes in light patterns over the course of the day, morning to evening. And in a couple of slides, I'll actually go into more detail about this as well. Also, the limitations, as I mentioned before, it's difficult to maintain consistent metrics, not just throughout the course of a spawning season, but over the course of time as well. And it's also difficulty to maintain volunteer involvement, with these groups. It's, oftentimes it requires a large number of individuals, a large amount of effort, and not just for the season, but over the course of time as well. So, as I mentioned before, these metrics, they don't account for changes in phenology. So actually, just to review, what is phenology? Phenology is the timing of certain life history events. And so you could think of different things, like in springtime, when, flowers and trees start to, grow leaves or the flowers begin to bud. That's an example of a phenological event, the migration of monarch butterflies. Or in this case, for river herring and for diadromous fish as well, a phenological event includes like the timing of the adult spawning migrations. And so the figures here, this is actually some research that was conducted by DMF and the University of Massachusetts Amherst along with the Northeast Climate Adaptation Science Center, where basically what we did was we looked at time series data of adult spawning migrations in 12 Massachusetts coastal rivers over time. And so these time series data ranged anywhere from 8 to 40 years, depending on the river system. And we looked at different phenological metrics. For example, like the date when the spawning migration began, the median date, which we would equate to, say, like the peak of the migration, the date when the migration ended, and then the duration, which is like the number of days between the start of the migration and when the migration ended. And so the results here are highly variable, but the take home message here was showing that over time, the results suggest that there are minor shifts in each of these metrics towards earlier dates in many of these runs. So in other words, many of our runs are actually slowly occurring earlier over time. And so because of this, because our count data is, because we are standardizing, the duration of our counts, like when they begin, when they end, that they don't necessarily take into account, dates and times when runs actually start earlier. And so for that reason, it's, the estimates are not, a total population estimate, rather it is an index. So I also mentioned that other limitations is that these metrics don't account for changes in deal migration patterns, which is basically looking at migration over the course of a day. And so here I actually have a couple of studies that were conducted by UMass Dartmouth, where they actually monitored daily migration patterns of river herring in two rivers. The one on the top is the Mattapoisett River, and the one on the bottom is the Herring River in Harwich. And so what they did was what their data actually showed was that that fine scale movements of river herring was associated between both, the time of day and in both of these cases, tidal stage as well. And so what they did find was that, they did find some areas where you see elevated activity during early morning as well as late afternoon, which we kind of refer to as those crepuscular hours. And so if you look at the table down below, what you find is that during the daytime period, which coincides with the general period for visual counting, that these two rivers, that the daytime period accounted over half to almost 2/3 of the total passage for the day occurred during the daytime hours. At night, passage accounted anywhere from 1/5 to 1/4 of the total passage during the day, and then during the crepuscular hours, which is basically like dawn and dusk, it accounts to up to 20% for these two rivers. So if you actually take our local example here, this is the Monument River. So this is the site that I manage and monitor using my electronic counter. Now, my electronic counter it can tell you how many fish pass over the course of the day. However, the counters don't inherently tell you when the fish pass. So in order to figure that out, what I did was I purchased an event logger and had it patched into the counter. And so what the event logger does is when the counter registers a fish passing through, the counter then relays a signal to the event logger, and then the event logger timestamps it so it can tell you when that event occurred or when that fish passed. And so here I have a graph that shows hourly passage over the course of the day. And the figure to the right is the same data, it's just displayed as a 24-hour clock. So the region in red is the daytime passage. So that's basically between the hours of 7 a.m. and 7 p.m., which again accounts for the daily time period used by most visual counting groups. The dark blue region, those are the crepuscular hours, so that's dawn and dusk, and then the light blue regions, that's overnight passage. And so I've been collecting this data for about over 10 years now, and so we see a pretty consistent pattern that almost two-thirds of passage actually occurs during the daylight hours, with about 12% occurring at night, and up to about 20, almost 25% occurring during the crepuscular hours. So next, I just want to go over some case studies here. So these next few slides, these are examples of runs that were reviewed and shown to have really good quality data. And so shown here are the run size estimates as well as the sampling coverage throughout each daily observation period, as well as the corresponding power analysis. Now, this first example, this is the Mystic River. This is in the Boston Harbor watershed. It's a 13-year time series. The map here with the red circle shows the sampling location. This is between lower and upper Mystic Lakes. This is actually referred to as a partial watershed index of abundance. The group here uses a two-way, three-period stratified sampling design, and because it's, as you can see on the graph below, this actually shows these are the daily observation periods and the numbers of counts that are conducted each period, and they're actually pretty evenly well represented here, and so its ability to detect trends over time is very strong, as shown by the power analysis below. And so up at the top, these are the indices of abundance. And so the red line on the graph actually shows the time series mean. And then what I did was I fitted a dotted line. It's a trend line. And then I conducted what we call a Mann-Kendall trend analysis. This actually shows if there's actually any identifiable trends within this data. And so the analysis was actually shown to be significant, and it was showing that over time, this population has been increasing over time. And so this data set was included in the most recent coastwide stock assessment update. Next here, this is the Nemasket River in Middleborough. This is a 21-year time series. And so this, again, is another partial watershed index of abundance. Now here, the group uses a two-way, two-period sampling design. And as you can see by the number of counts per hour throughout the course of the day, a lot of it tends to be centered towards the middle of the day. However, over this 21 period, this has been consistent. And because of that and the large volume of counts that they conduct, it produces a very strong power analysis here. And so the trend analysis here seems to indicate a light increasing trend over time. The next one, this is a local example. This is Townbrook in Plymouth. Again, this is the sampling location here. I would regard this as a partial watershed index of abundance, even though it's very close to Plymouth Harbor. So it's close to being a full watershed index. But based on our biological sampling, we know that alewives, pass through the gristmill ladder, which is where the sampling station is located. The blueback herring, however, they stay downstream of this area. So we know it's not a total, the estimates are not reflective of the total population. So it's a partial watershed. This watershed has undergone extensive restoration efforts as well. And so for this reason, we also think of it as a restoration response too. They also conduct a two-way, two-period sampling design. But because of that and the large volume of counts that they do, their estimates have high predictive power. And actually, when I conducted the trend analysis for this last year, 2 years ago, it actually showed a significant positive rising trend over time. It's just, unfortunately, last year, they had a significant drop. And so with that, it actually, the Mann-Kendall trend analysis wasn't no longer consistent. However, it is still indicating low to modest increase in the population over time. And so this one, too, has also been included in the most recent stock assessment update. So our last case study here, this is the Marston's Mills River here on the Cape. And so they actually have two counting locations here. The lower one, which is Mill Pond, this is a 13-year time series. It's a partial watershed index of abundance, which they use a two-way, three-period stratified random sampling design. And in 2018, following fish passage improvements in the upper part of the watershed, they started a second count here at the outlet to Middle Pond. And so this one I would refer to as a restoration response. And so if you look at the table here on the right, this actually shows the estimates for both Mill Pond and Middle Pond. And so because they're conducted using the same sampling design and using the same method, you can actually estimate the proportion of fish that were being counted at Mill Pond, making it all the way up to Middle Pond here. And so over the course of these 7 years, what they're showing is that anywhere from 46 to almost 100% of the fish in a given year that are being counted at Mill Pond are making it all the way up to Middle Pond. So it's a way of documenting the success of the restoration, the efforts that they did in the upper parts of the watershed. So I'm just going to just summarize and provide some recommendations here. So just to summarize, visual count estimates, these are indices of abundance, and they're not, reflective of the total population, or they're not true population estimates. And the type of estimate that you're looking to obtain will be determined largely by the location where you're sampling. The counts, in order to be able to utilize them to identify, changes in population size over time, they have to be conducted using consistent protocols. And so for that, we recommend maintaining consistent metrics for abundance estimation. Avoid, aggregate or cluster sampling. And then this next part, I put it in red and in bold. It says zero counts are important data. Basically, what it is that, for many people, they say, well, I go to a run and I constantly go and, I never see anything. Well, I mean, even though you're going there and you're not seeing anything, that's still very important data, because the reason being is that it helps us to identify, the nature and behavior of these fish. We know that, their migrations don't follow a consistent pattern. And so it can help us to determine, what could be influencing, their behavior and these patterns in migration. Could it be something associated with water temperature? Depending on the location of your sampling station, is there a tidal component to that? Is there a tidal influence that's driving their migrations as well? So that data is still very important. I can't stress to you enough how important it is to, even if you don't see any fish, to still go out and collect that data. And so we recommend maintaining these, consistent metrics to maintain the integrity of existing counting programs. As I said, visual counts have limitations. They have inherent biases and error associated because you have to extrapolate your estimates based on sampling. They don't account for changes in phenology or DO movement patterns. But despite that, we still recommend that groups go out and count once, herring are first observed, because that data is important to document any changes in migratory patterns over time. And as I mentioned before, establishing and maintaining visual counting programs is difficult. It's challenging to establish and maintain volunteer effort, as well as to maintain, a random sampling schedule. And to do that year after year, is difficult. And so next, the last thing I wanted to touch upon here is counting at night. Because we have been approached, by several individuals that, say, hey, I want to count at night. Why don't you recommend doing this? The reason being is, well, there's several reasons for this. I mean, one, it is difficult to maintain volunteer effort just in a normal counting group. But, but to expect people to go at night, that I think you're asking even more from people to do that, because there's a lot of issues associated with counting at night. Issues with visibility. Being able to see well into the water, and you know, and if you see fish into the water, being able to properly identify whether those are river herring or not. Because in these systems, river herring aren't the only fish that are moving, back and forth. There are other fish that do that as well. So, there can be issues with identification. Certainly issues with safety, especially if an area is remote, it's dark, or it's in the middle of the woods, or even in places, that are, more highly visible. If I think of Great Herring Pond, you know, the counting station is at the crossing at Little Sandy Pond, just downstream of the outlet. It's a dirt road that does get a fair amount of traffic, and there's no parking lot really there other than, where the boat launch is. So to park over there, and then you got to walk over and you got to walk along the street to get to the counting station, you know, there's safety issues associated with that. So, obviously you don't want to put people in harm's way or potentially in harm's way to do this. Um, Now, when I've talked to people who are counting at night, I say, well, how do you see the fish? And they say, well, I break out my flashlight and I shine it in the water and I look for them. Well, several studies have also shown that, artificial lighting is shown to affect, the behavior of fish and their natural migration patterns. I mean, ideally, we're looking to conduct, these counts to observe fish as they're migrating under, natural environmental conditions. And so if you think about it, if you're a fish and you're sitting, in water and you're sitting there, you're holding, you're holding position at nighttime and you're waiting for dawn, to move. Suddenly, you see a bright light being shined upon you. Well, yeah, you're going to move because, you don't want to be predated on. So, basically, artificial lighting is shown to affect their natural behavior. Um, and because, people oftentimes, they are seeing, this increased activity, especially during these crepuscular hours, it also introduces that temptation to tailor your sampling more towards those times to see the fish. And so that also, goes down the road of, aggregate sampling, which we want to avoid that. We want to randomize it as much as we can. And so for these reasons, the estimates that are derived from visual counts, we classify them as indices of daytime abundance or daytime passage. And so with that, on behalf of the Division of Marine Fisheries, we want to thank, various groups and organizations and individuals for their efforts over time to assist us with this monitoring effort. They come from, the federal government to, non-government and private organizations, local watershed groups, and municipalities as well. But most importantly, volunteers. You folks, you're our eyes and ears on the water. And because of you, Massachusetts has one of the most extensive monitoring networks for river herring populations, as evidenced in the 11 rivers that are represented in the coastwide stock assessment. That's in big thanks to citizen scientists. And so for this presentation, I used a few references here. These are available. Well, these were available on our website, but we actually had to take the PDFs down because of new digital accessibility requirements. So eventually, we hope to get these back up on our website, where you can just go and you can just click on the link and you get a PDF version of these. But if you are interested in any of these references or publications, I left my email there. Feel free to contact me, and I'll be happy to email you any of these documents. Also, one of my colleagues, his name is Mike Palmer. He is a regional volunteer herring count coordinator for Cape Cod. He works for the Association to Preserve Cape Cod, and so he oversees several volunteer groups throughout the Cape. And so what he did was he actually just created this interactive web tool, which basically explains and demonstrates the principles of visual counts and why you want to randomize your counting and how you can produce different results based on the different ways you choose to conduct your counts. And so the web link is shown here. It's actually it actually just came out last week, and I had a chance to play around with it for a little bit. But it's actually a pretty neat tool to kind of explain the different statistical concepts and how the way you conduct your counts, how that can affect your results. And so finally, I just wanted to also spread the word. The call for volunteers to assist with the visual count at Great Herring Pond. And again, Lynn's contact information is shown here. So anyone's interested, you can please contact her. And so with that, I really want to thank all of you for your time and thank you all for listening.
Thank you, John. Super excited to learn more with you, and I hope that we are ready to help volunteer with this annual herring count this year.